So we're finally at section 6.5, which is the last bonding section that we have, and it primarily focuses on what we call VSEPR theory, and VSEPR theory maybe isn't an accurate pronunciation of this acronym, but it's valence shell electron pair repulsion theory. So I have a few things scattered around here on the board. Let's take a look here first at what the definition of VSEPR theory is. So when we talk about valence shell electron pair repulsion, what we're talking about is we're using this theory to predict the shapes of covalently bonded molecules, ions to some extent, but primarily covalently bonded molecules. So what we think of is that these outside electrons or outside electron pairs, well, they're negative. So our electron shells are negative and they're repulsing each other. And when they repulse each other, what they want to do is spread out as much as they possibly can in three-dimensional space so that those electronic repulsive forces are minimized to the greatest extent. So when we look at what we have in a bond, what we have shared pairs and we have lone pairs are what we're looking at. So here's our first example. It's kind of tough using a first example being an exception to the octet rule, but that's right. So we have beryllium fluoride, which is an exception to an octet rule. And we want to figure out its geometry. And this one is pretty clear. So what we have is this fluorine that has an electron cloud, and this fluorine that has an electron cloud. And what they're doing is they're repulsing each other. So these electron clouds, and in fact, even actually it is the shared pairs between them themselves are actually repulsing each other. So these fluorines are not going to be right next to each other. They're going to be spread out as far as they possibly can in space. So we're going to have one fluorine with its lone pairs on one side, one fluorine with its lone pairs on the other, with beryllium in the middle. So they are going to be what we call 180 degrees apart. So if we drew them across a circle, they would circumvent this, they would cut the circle in half, so they're 180 degrees apart. This type of shape is called linear. So when we're looking at the molecular geometry, if we have two shared pairs on an element, and that's all we have, well, the only option we have for a shape is a linear shape. There's really nothing else we can do with this. Another common place where we see linear geometry is with a structure called CO. So with our carbon dioxide, our structure CO2. Now, CO2 is a little different in that it has two shared pairs here, but they're still repulsive. They're still full of electrons, and those electrons are repulsing the electrons on the other side. So these two shared pairs, and again, even though they're double bonds, are repulsing each other. So it is still going to have a 180 degree bond angle, and we'd still give it what's called a linear shape. Now, if we build it with a molecule kit, this is what we'd get. We'd get a linear shape. Now, if we add another atom to that central atom, and again, this is another exception to an octet rule, but we can look at it because it's good to look at some of these as far as when we're starting with shapes. And so now we have boron trifluoride. And again, 1, 2, 3 shared pairs, or what we might call 3 negative charge centers. If we have 3 negative charge centers, again, those things are going to try to spread apart from each other as much as they possibly can in space. So we have our boron here, and again, this is an exception to the octet rule, so boron has no lone pairs. But we have fluorine with its lone pairs, fluorine here with its lone pairs, and a fluorine over here with its lone pairs, all of which are repulsing each other. If you spread 3 things out as far as possible in 3-dimensional space, what you are going to get is a bond angle between each of these of 120 degrees. So these are all spread out at 120 degrees. This shape, by the way, is called trigonal planar, because it is flat in a plane. This is a flat molecule, trigonal, because there's 3 bonds. So the molecular geometry, when we have 3 negative charge centers, is trigonal planar. So just like with CO2, we do have another example of this that's not an exception to an octet rule, and that is CO3. So this is an ion that's covalently bonded. It's our carbonate ion. If we drew out its Lewis dot structure, it would look like this. Now it has 1, 2, 3 negative charge centers. Again, even though that's a double bond, it comes as 1 negative charge center. So they're going to spread out as far as they possibly can in space. That's going to give this a bond angle of 120 degrees. So still trigonal planar geometry and trigonal planar molecular geometry. Now, if we add a 4th bond, this is where things maybe start to get a little bit more interesting. So this is methane, which is CH4. And this would be a proper representation of its molecular geometry. So notice what's happening here in a proper representation of its Lewis dot structure, really. Notice what's happening here is now we've actually kind of left a two-dimensional world and we've gone into a three-dimensional world. Our other structures could be well represented two-dimensionally, but this one really cannot. Because if we have four negative charge centers, they're going to try to spread apart from each other as far as possible in three-dimensional space. So this cannot be flat. Initially, people like to think this is flat with bonds 90 degrees apart. That doesn't make any sense because this can spread out three-dimensionally, so it does. And if you cut the space three-dimensionally, what you'll find is that each of these is 109.5 degrees apart. 109.5, 109.5. So any way we turn this, every bond is separated by this magic bond angle, 109.5. So we had 2 negative charge centers for a linear shape, 3 negative charge centers for a trigonal planar shape. Now we have 4 negative charge centers, and we are going to have a tetrahedral shape. Now notice with tetrahedral it gets interesting because tetrahedral is based on our number of negative charge centers. So the number of negative charge centers in tetrahedral shape is 4. Now notice for methane here, it has 4 shared pairs, but it doesn't have to have 4 shared pairs. It could have any combination of, this is our shared pairs, and this is our lone pairs. Because one important thing we need to remember about valence shell electron pair repulsion theory is that our lone pairs take up space as well. And in fact, lone pairs actually take up more room than a shared pair because they're not bonded. They're not being kind of held down. So they have more room to spread apart and actually have a stronger repulsive force. So the general shape of all of these, the molecular geometry, based on its negative charge centers, we would call tetrahedral. But they have different shapes. So the molecular geometry is tetrahedral. For methane, the shape is tetrahedral. For something like this, ammonia, which is NH3, if we draw out the Lewis dot structure of it, notice it has it over here. And again, they are going to use three-dimensional representations of these. So this little black triangle represents it coming out. The dotted one represents it going back into the piece of paper. This is the only way we can try to draw two-dimensional structures or three-dimensional structures on a two-dimensional surface. This is our lone pair that's, again, taking up space. So the basic geometry is still tetrahedral, but the shape now we call trigonal pyramidal because there's 1, 2, 3 bonds, and that lone pair pushes them down into a pyramid shape. And actually, if the bond angle here is 9.5 degrees, this bond angle now between the hydrogens is actually a little reduced because that lone pair takes up more room than a shared pair. The bond angle is actually about 107. Now, notice down here, this is water, H2O. If we draw out the Lewis dot structure, we'd get this. And what water has on it is 2 shared pairs. These shared pairs, again, take up actually more room, or these are lone pairs take up more room than our shared pairs. And so the bond angle now between my hydrogens has been reduced even further to about 104.5 degrees in water. And so one thing we'll see with these is, one, the important thing is lone pairs take up space, just like shared pairs. So when we're trying to predict the shape or the molecular geometry of these, we do have to include and count the lone pairs as if it was a shared pair. But those lone pairs actually even take up a little bit more space. So we get a general tetrahedral geometry, but the actual shape will be a little bit different, and the bond angles will be a little bit smaller the more lone pairs we have in the structure. So this is just another image of water. Again, water, when we draw its Lewis dot structure, is going to have these 2 lone pairs which push down on these hydrogens, making that what's called, actually, if we look here, this is actually called a bend shape. So it's tetrahedral geometry, but a bend shape is what we'll refer to it as. So it's tetrahedral geometry, the shape is bend because of those lone pairs. Now we have our basic geometries down. We have linear geometry, and linear geometry is really a linear shape. There's really no other options. Trigonal planar geometry, we can have a couple small variations. We can have a bent variation of that. So we can have, I believe, SO2. If we draw out SO2, it's actually like this. Sulfur dioxide. Sulfur dioxide has a lone pair, so that takes up space and it bends these bonds down. So it has trigonal planar geometry because it has 3 what this is calling a steric number, or negative charge centers, 1 for that bond, 2, and then the lone pair here. But the shape is actually a bent shape, and we'll look at the shapes a little bit more later on, so don't worry too much. Right now we just want to get the charge, the predicted geometry down. So anytime we have 4 negative charge centers, whether they're shared pairs or they're lone pairs, we're going to have tetrahedral geometry, and CF4 or CH4 is the general description of this. But again, we can also have water in this category. We can also have ammonia having this tetrahedral overall molecular geometry. Obviously, we have different names for the actual shapes. And going down from that, now we have a couple of others that we probably should look at, but do know that these, again, are exceptions to the octet rule, so we won't see them a lot. But if we add in one more bond, a 5th bond, then we get trigonal bipyramidal. The bipyramidal is 2 pyramids. There's a pyramid on top if we connect these, and there'd be a separate pyramid on the bottom. So it's bipyramidal, trigonal bipyramidal. And the classic example of that is PF5. So it's adding in one more bond, adding in yet another bond, gives us a shape called octahedral. Octa means 8. So it's octahedral because if we connect all these bonds and look at the surfaces of them, there'd be 1, 2, 3, and 1 on the back, 4 planes on the top, 4 planes on the bottom, for 8 planes in the structure for an octahedral shape. And all of these are separated by 90 degrees. Sulfur hexafluoride is our classic example of an octahedral shape. So this is probably a good summary of what we have right now. So our spatial geometry, if we have linear, they have bond angles of 180. And really we have, let's put down our number of charge centers. So it has 2 negative charge centers, and only 2 negative charge centers. Trigonal planar, 120 degree bond angle. Here's a bent is another option of it. So that's a shape. So this is the geometry. This is one of the shapes that we can have. Again, that happens when we have 3 negative charge centers. Again, just like this shows, it could be 3 bonds or it could be 2 bonds in a lone pair. Here we have 4 negative charge centers. That's going to give us a tetrahedral geometry. Our general, again, bond angle is 109.5. Like we've talked about, though, if we have ammonia, that's trigonal pyramidal, or water, which is bent, we're going to reduce that bond angle. Also, again, notice we have trigonal bipyramidal, which we just talked about when we have 5 negative charge centers. Now, we could replace lone pairs into any of those negative charge centers, and we get slightly different shapes. We don't have to worry about memorizing the shape names of linear or T-shaped or sawhorse, but those are out there. Those are kind of renegade shapes that are out there. Octahedral again, and if we replace those bonds with lone pairs, obviously we get slightly different shapes, which have some slightly different names. What we want to look at, though, a little bit closer is how these shapes actually originate. Because remember what we talked about before when we talked about the electronic structure is we talked about s orbitals, which were spheres, and we talked about p orbitals, which were dumbbells that were orientated along the axis, correct? We had a PZ, we had our PX, and we had our P, we left Y. So we had those orbitals, but notice we don't see a lot of bonding that is right along axis points in 90 degrees. We do see that here in our octahedral shape, but that's not kind of the go-to shape. So something else is happening when things bond. That's giving us these different molecular geometries, and what that is kind of this theory of hybridization of orbitals, orbital hybridization. So when we have orbital hybridization, the example that's being shown here is for carbon. So carbon has 4 valence electrons. It has 1 in it actually has 2. Sorry, let me start this over. So carbon does have 4 valence electrons, and generally we write it as 2s2, 2p2 for carbon. Well, when carbon bonds, what happens is one of those electrons, notice, gets excited up into the p level. The other thing that happens is the energy of the p level, when it goes into bonding, comes down slightly, and the energy of the s level gets excited a little bit. And so what we get is what's called an sp hybridized orbital. Now notice it's called sp3, and you might have noticed those labels on the previous page, sp3, because there's 1 s and 3 p orbitals combined in this hybridization process. So it's one s orbital, 3 p orbitals involved, so we get sp3 hybridization. Now notice what that is showing us. That is showing us that carbon has 1, 2, 3, 4 locations for bonding, which here now starts to make a little bit of sense. So what we were talking about before, again, was the sphere shape and these dumbbell shapes. But again, when we put them together, we get what is called these hybridized orbitals. And so when we look at hybridized orbitals for a carbon, and again, this only happens when it's involved in bonding. When it comes and starts interacting to bond, then those orbitals hybridize. And we have carbon here, and notice it has 1 electron in each of these hybridized orbitals. And notice it has tetrahedral geometry, which is what we actually find when we look at the shapes that carbon is bonded in. So now along each of these axes, it can combine with, say, a hydrogen here, a hydrogen here, a hydrogen here, and a hydrogen here. So methane has a tetrahedral shape. The reason it has a tetrahedral shape is because the carbon electronic structure hybridizes when it comes into contact with something in which it's going to bond. Now notice anytime we have that tetrahedral molecular geometry, it is an sp3 hybridized. So this is nitrogen, and again nitrogen bonding with hydrogen. Now nitrogen has 2 s orbitals and 3 p orbitals, and we might just think those p orbitals are involved in bonding, but really that's not true. What we get is actually 4 equal hybridized orbitals, where we have one of those hybridized orbitals completely occupied by a lone pair, and the other ones are the ones involved in bonding with hydrogen. So there's still, anytime we have tetrahedral molecular geometry, we're going to see sp3 hybridization. So that's true for methane, right, which is true tetrahedral. That's true for ammonia, which is trigonal pyramidal, but again still has tetrahedral geometry, and that's also true for water. That again, water has tetrahedral molecular geometry because it has 4 negative charge centers, but we call it a bent shape. So its orbitals also are being hybridized in the process. Now, despite that, we do not always have to have sp3 hybridization, and perhaps you've noticed that because not all of our shapes have tetrahedral molecular geometry. Now, if we combine 1 s orbital with just 2 of our 3 p orbitals and leave 1 p orbital unchanged, then we get something that's sp2 hybridized because there's 1 s and 2 p orbitals involved in that hybridization. Now, if we have an sp2 hybridized orbital, what we're going to see is trigonal planar geometry. Now, one thing, if you remember that we talked about that could be trigonal planar geometry, is sulfur trioxide. So we have sulfur, we have an oxygen out here. So SO3 is something that it has a classic trigonal planar geometry. It has 3 bonds, 3 negative charge centers, and these things are repulsing each other, and we get this 120-degree bond angle. So anytime we have that trigonal planar geometry, what we say is that is sp2 hybridized, 1 s and 2 p orbitals involved in the hybridization. Now, where is that unchanged p orbital? Well, that unchanged p orbital is actually this double bond right here. So double bonds actually exist outside. They're not right between the nucleus of the atoms. They're not right between the sulfur nuclei and the oxygen nuclei. They actually exist slightly outside that nuclei. So our hybridized orbitals are right between the nucleuses, but this p orbital is actually looking and behaving like a p orbital. So whereas these are hybridized, and they're right along these axes, right here, just like it shows in the picture. I shouldn't try to redraw it. This p orbital is floating kind of above and below that nuclei. Same thing with, there's a p orbital in the oxygen that's being involved as well, and they are sharing that electron across that space that is outside of the center of the nucleus a little bit. So it has 1 p orbital that's involved in bonding, but it's not hybridized. It's acting like a p orbital. It has the normal shape of a p orbital, aligned in kind of a similar direction that we might see for a p orbital. So anytime we have 3 negative charge centers, we're going to have trigonal planar geometry, and a lot of times that extra p orbital is actually going to be still involved in the bonding, but often it's going to be in the double bond. And so anytime we have single bonds, these hybridized single bonds, we're going to start to refer to as sigma bonds. This is the symbol for sigma. Anytime we have double bonds, our double bonds, we're going to start to refer to as pi bonds. So here's just another image of sp2 hybridization. So we have one s and two p orbitals that have been hybridized into these three lobes, and we have our p orbital that's non-hybridized, and so it can still exist, be present, and typically be involved in a double bond. One last type of hybridization we'll look at is sp hybridization. As you might be able to tell, sp involves one s and one p, so we get two lobes of hybridization. And so typically if we have sp hybridization, we are just going to have a linear shape. That's all it's going to allow us to have. Our classic example of this is carbon dioxide, which is linear. It is sp hybridized because there's only two negative charge centers. And notice what it has. It still has these double bonds, right? It has a double bond here, double bond here. Well, those double bonds are existing from p orbitals that have been unhybridized. So there's p orbitals that are sharing electron density that way, and p orbitals that are sharing electron density either above or below the center of the nucleus on this side as well. So just going back to this image here, it's a good one to study. So linear geometry again, 180-degree bond angles, sp2 hybridized, or sp hybridized. Anytime we have two negative charge centers, anytime we have three, it's going to be that sp2 because there's one s and two p orbitals involved in the hybridization. Again, tetrahedral, which is again our most common shape. We're going to see a lot of structures that have tetrahedral spatial geometry. They're always going to be sp3 hybridized again, even if they have those lone pairs in them. 1s and 3p have been hybridized to make that overall molecular geometry shape. And notice what happens when we have these expanded octet type of shapes, these ones that are exceptions to the octet rule. What's happened is they've actually gone into the D shell for hybridization, so it's really crazy. So if we have 5 negative charge centers, well then we don't just have the sp3, which gives us 4, we also have a D involved. Obviously if we have 6, 1, 2, 3, 4, 5, 6, then we have 1s, 3p, and 2d for a total of 6 hybridized orbitals for bonding.